Vinícius is going to talk about the traditional portfolio approach, but bringing in something very interesting, in which, by the way, we are doing research at the moment, so it's very interesting. So yeah, go ahead, Vinícius.
Sure, thank you. Can you hear me well? There is some. I'm gonna apologize first because I guess there is some disturbance around. But if you can hear me well, I'm just gonna get started without further ado. So I'm gonna be talking about risk parity, which is a topic that you've seen already. But I'm gonna be introducing these hierarchical models, which is a different way to do risk parity with a little bit more fancy techniques. So we're gonna have the following agenda in our talk, right? I'm gonna start by introducing Markowitz, which you all are familiar with that, and then the classical risk parity portfolio, some historical events, and the convex formulation that you should know very well, and the non-convex one as well. And then I'm gonna show some examples on Python and R with some solvers that we've developed in the past months. And then finally, I'm going to introduce hierarchical risk parity and what is all the fuss about it. And we're going to see an example on very recent data, data that was affected by the COVID-19 pandemic, and we're going to see how this portfolio performed. I guess you're going to be surprised with the results. And then finally, some closing thoughts. But yeah, without further ado, let's go for it. So first, the question, right, that portfolio optimization tries to answer is how to allocate some amount of money into some number of assets, right? So if everything is Gaussian, then we can write down the expected return and the variance of our portfolio, just like that. And then in 1952, Dr. Markowitz proposed this optimization program that made him win the Nobel Prize in 1990, right, in economics. So it was quite an impressive work. And it's the beauty of Markowitz is that it's really straightforward to understand, right? Because you want to maximize the expected return of your portfolio while at the same time minimizing some measure of risk. And in this case, the variance was used as a measure of risk, but you've seen, I guess, 2 lectures ago that there exist other measures of risk, probably even better than the variance. But as once a famous physicist said, if your theory is really beautiful, but it doesn't work in practice, then it's a bit useless, right? So unfortunately, that's what happened to Markowitz's theory. I mean, it's not useless by no means, but practitioners have seen that it doesn't work very well in practice if you just use it as it is, right? As the vanilla, the basic Markowitz approach. It's not very successful. You've seen that on the homeworks as well. So basically, the main reasons for that, sorry about that, is the sensitivity to mu and sigma, right? It's very sensitive. You change mu slightly, you're gonna get a totally different position. You change sigma slightly as well, things just go crazy. And it doesn't consider risk diversification, right? We see whenever we build a Markowitz portfolio, we see that usually the money is allocated to just only a few assets, which is not good in practice, right? So that's why risk parity became very popular because of the ineffectiveness of like Markowitz and other portfolio approaches as well, right? So risk parity is basically a change in philosophy, right? It becomes it's different. You want to allocate the risk of your portfolio rather than the money directly, right? So you want to see the same problem through a different lens, pretty much. So the first risk parity fund was created by the Bridgewater investment fund in 1996. So differently from Markowitz and other portfolios, risk parities, it was built on the industry pretty much. So they built that in 1996. And in 2004, they published a white paper telling everything about risk parity, how it works, and how you could implement it yourself. And then in 2011, after 2011, risk parity became very popular, especially after the crisis in 2008, that practitioners and investment funds saw that those who were following the risk parity approach were more or less robust to that crisis. So risk parity becomes a thing pretty much after 2011. And the basic idea that you all already know is that we want to design a portfolio such that the risk is equally distributed across the asset classes or distributed according to some predefined risks, right? And that's what we want to see, right? In when we compare risk parity with, say, Markowitz. We have here the weight allocation on the top chart. We can see that risk parity is much more diversified than Markowitz, and the relative risk contributions are all uniform. So that's what we want to do. And just a little bit of review of the technical part. I know that you know that, but let's just pass through it really quickly. So we start by decomposing our measure of risk. In this case, I'm gonna use just the volatility using Euler's theorem, right? And then the derivative here of the risk with respect to the weights is called the marginal risk contribution. It basically says the rate of change of the risk with respect to the weights, right? With respect to the amount of money that you put in that particular asset. So you can use the same, you can do the same approach with different measures of risk, VAR and CVAR that you've seen a couple of classes ago. And then we can define some additional quantities here that are going to be helpful on our understanding. So the risk contribution is just the amount of money times the marginal risk contribution, right? And then from Euler's theorem again, we can see that if we sum with respect to all the stocks, we're going to get back our risk measure. So that's good. And then what we want to do ultimately is to use the relative risk contributions. That we just normalize the risk contributions by the total risk pretty much. And then that's what we want to achieve, right? So we want a portfolio, we want to find a portfolio such that the relative risk contributions are equal to some predefined vector B, the risk budget vector. And it looks crazy, right? This problem looks a bit crazy to the unexperienced eye. But then we can start to see some edge cases. For example, what if the covariance matrix is diagonal? Then there is a closed form solution to this problem given by this expression, which is our famous inverse volatility portfolio. And then in 2013, this researcher, Espino, he came up with a brilliant idea. He pretty much saw that after a slight change of variables, the risk parity problem becomes this fixed point equation here, right? And then this fixed point equation is nothing but the optimality conditions of this objective problem, right? The first order optimality conditions of this convex problem. It's insane, right? It couldn't get better than that. So basically, it's convex. We know how to solve convex problems. Just call a solver in Python, CVX, for example. But then, yeah, we can see that it's not one of the convex problems that we are more familiar with. It's not a QP. It's not an LP. So that was the need for a nice algorithm, pretty much, to solve this problem. And here's the CCD, cyclical coordinate descent algorithm to solve this problem. I guess you've done this, you've implemented exactly this algorithm on the last homework, if I'm not mistaken. And to to the extent of our knowledge, this algorithm is the fastest algorithm to obtain the solution for this convex risk parity problem, right? So, but then in practice, right, practitioners, they want to include additional objective terms or additional constraints such as box constraints or the expected return, and then it doesn't work anymore. That convex approach doesn't work anymore. But then in 2012, these two researchers proposed this non-convex problem, so that you can include additional constraints and additional objectives. But there is a problem, right? How do we solve this non-convex formulation? It gets tricky. Well, one way is just to use general solvers, right? Everyone knows how to use the minimize function from the spicy, how our professor likes to call the SciPy library. So everyone knows how to use that. But then in 2015, these two researchers, Fang and Palomar, they proposed, they identified that the many non-convex formulations of the risk parity problem can be written in this framework here, where you have a function that is squared and then some additional function assumed to be convex. So the idea is that you convexify the non-convex term, in this case the function g here, and by convexify I mean you find a linear approximation to that function g, and then you just you solve iteratively, like using the SCA framework that you also have seen in this class. So they come up with this idea, and it's a really good algorithm, and we have written that. We have implemented that algorithm in Python and in R. In those two packages, I guess you've played with the Python version, but there is also an R version if you are keen on using R. And now I'm just going to show a really quick example on how we would go about using these packages, right? In R, it's really simple. You just import the library, and then you just use the function risk parity portfolio, where you pass two arguments, one of them your estimate of the covariance matrix, the other one the budget vector of your portfolio, the desired budget vector, pretty much. In Python, it's quite similar as well. You just import the package and create an object from the risk parity portfolio class, passing the covariance matrix and the budget vector, and then you use the method design. Then you can pass additional arguments, whether you want to include the mean return or the variance in the objective terms. And then you can get the weights using the property weights here and the risk contributions. So let's see a more practical example, right? Here I'm downloading, this is R code, right? So I'm downloading data from 5 stocks from these FANG companies here, and I'm going to use this package called portfolio backtest, which will do many rounds, right, of many tests pretty much on the portfolio, and see, like, we will compute the Sharpe ratio and all those quantities that we are interested in. So basically what the philosophy in this package is, basically you create a function that takes in a data set and spits out a portfolio. So I just create, it's basically a wrapper, right? I create a wrapper around the risk parity portfolio function, where I just get the data set, compute the covariance, compute the log returns and the covariance matrix of those log returns, and spit out the portfolio. And then I call the portfolio backtest function, where I pass the functions to be tested, the functions that return the portfolios, the data set, and some other additional parameters like the rolling window or the frequency of rebalancement and so on. So let's see how so here I'm comparing, right, the risk parity with this tangency portfolio. Tangency is another name for the maximum Sharpe ratio portfolio that you all are familiar with. So here we use this function backtest chart stacked bar to see the evolution, to see like how our portfolio evolves over time. So each bar here is pretty much the amount of money that I'm putting in each stock. And you can see here that for the tangency portfolio, everything looks really crazy, right? In some period, you have only Apple and Facebook, and then 3 periods later, you have only Amazon and Netflix on your portfolio. So that's kind of not ideal because we're going to spend a lot of money in transaction costs, and it's also not intuitive, right? We don't expect the portfolio to change too much in such a short amount of time. Here's the result for the risk parity portfolio, which is much more intuitive. Things are much more well behaved. It's pretty much a uniform across like 4 years, right? It doesn't change much. Okay, there is some changes here on Facebook, and so, but it's pretty much uniform, which is good because we don't have to change a lot our portfolio. So here is the money plot. Here's how much money you would make if you use that strategy. If you use the risk parity, you would make a lot more than the maximum Sharpe ratio portfolio. So that was basically our review of risk parity. So the good thing about writing open source code is that not only people can benefit from, but they can give us some feedback, and it's good. We want to improve the code, and some people have used our packages, like this guy here from Chicago, and this other guy from 2 Sigma in New York, and it seems that our packages have been useful, so that's a good thing. It's always good to get feedback from people working directly in the industry. So, okay, let's go for hierarchical risk parity. But before, there will be a little bit of graph theory, because that's what risk parity it's built on top of. So I'm just gonna pass a little bit quick, but I'm gonna make sure we understand what's going on here. Right? So basically, a graph is just this mathematical structure which has a vertex set V, which is just a list of pretty much is a list of integer numbers or labels. You want to label the nodes of your graph, right? And then there's this edge set, which is a subset in which every element is also a set, right? Containing 2 elements belonging to the vertex set. So what it means is that if there is an element here of this set that contains this pair, then there is an edge between 2 nodes, right? So that's what the edge set means. And then more importantly, there is this adjacency matrix, which is a square matrix with the following properties. It's 0 along the diagonal, which means that there is no self loops in the graph. And then the ij element is positive if and only if this set here belongs to the edge set. Otherwise, it's 0. So pictorially, here's a representation of a graph, right, with a few nodes, and you can see the weights represented by the elements of the adjacency matrix here around. So there is a very particular graph called a tree graph, which is a fully connected graph such that the number of elements in the edge set is equal to p minus 1. Basically, you have p minus 1 edges, and it's a fully connected graph. Right? So here are 2 pictorial representations of a tree graph. On the left, we have the graph itself, just like the visualization before, and here we have a dendrogram, which is like a view of the tree with this sort of like a clustered view, right? You see that, for example, nodes in here are clustered together, and then pretty much it looks like a tree, right? You can see that there is some hierarchical structure that is going from a top down, basically a top down approach. Yes, so then there is a particular interesting tree, which is called a minimum spanning tree. And the definition of a minimum spanning tree is basically a tree that spans the whole graph, which means that for any two nodes in a given graph, there will be a path connecting those two nodes. So that's what the span of a graph, what spanning a graph means, right? And then it's minimum because it minimizes the possible the sum of the edge weights, right? So basically, on the right hand side here, I have a graph which is of course not a tree, and it's not a minimum spanning tree. But if I ask you to find the minimum spanning tree of this graph, if I tell you that the widths of the edges are inversely proportional to the weights, then it's easy to find just by eye the minimum spanning tree, right? And the minimum spanning tree, it's unique if and only if all the edge weights are also unique. And why all this graph theory, right? Because so before let me explain how you would go about. There are many algorithms to find a minimum spanning tree. One famous one is this cross-call algorithm, which pretty much you start with an empty graph, and then you check whether two nodes are connected. If they are not connected by a path already, which you can do that using different algorithms, then you add that node to the graph, and then you loop through all possible nodes. Then you're gonna get the minimum spanning tree at the end. Okay, you need to make sure that the order in which you loop, it's by increasing distance, right? So basically, the hierarchical risk parity idea became famous because, well, we know that portfolio theory, the modern portfolio theory, is sensitive, right, to estimation errors of mu and sigma, as we already know. But there is some alternatives like robust portfolios, as you've seen like in the last class, or Bayesian priors, or improving the estimators of the covariance matrix, like using Ledward-Wolf, for example. But then the HRP idea, the hierarchical risk parity idea, is to exploit this clustered nature of stocks, right? Because we're gonna build so we're gonna see how hierarchical risk parity allocates the weights. It's basically using a top-down fashion, just like how practitioners would do, right? You would first think about which industry you want to put your money in, and then you would go on the sectors, which sectors you would want, and then you would go down to the individual assets eventually. So hierarchical risk parity was proposed by Lopes de Prado, a very famous quant researcher, in 2016, and it's basic. It's a basic idea, although it's a little bit heuristic, as you will see, and it follows basically two steps, right? You build a minimum spanning tree based on this distance matrix, where Ij here is the correlation is the estimated correlation, whatever correlation you estimated between stocks I and J, and then you use this recursive bisection algorithm to allocate the portfolio weights, which is what we are interested in, right? So basically, we built the minimum spanning tree based on these distances, and then we're gonna have the dendrogram, right? Gonna have the dendrogram, and then we're gonna see the order in which the stocks were allocated. So here's the algorithm for the recursive bisection. I'm not gonna dive too much into the details here, but I'm just gonna try to explain in a high level. So basically, you divide the stocks that you have, ordered according to the minimum spanning tree, and in two chunks, right? You start dividing into two chunks, say the left chunk and the right chunk. And you would expect that those stocks will be clustered, right, as we saw in the previous dendrogram. And then on each chunk, you give some amount of weight to 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 to, to those chunks of stocks, right? And the way you allocate the weights is basically using this splitting factor alpha here, which is computed by this ratio here of sigma tilde 1 and sigma tilde 2, which is basically the variance of the say the left chunk of stocks and the right chunk. And then you allocate this amount of weight on one chunk, and then you allocate 1 minus this amount of weight in the other chunk. And then you keep chunking the chunks into half until eventually you only have like one, until you only have one stock per chunk, and then that's it, the algorithm stops. So basically, if I would go to explain pictorially here, I would, for example, divide the dendrogram here, or more or less on the half, and then I would allocate half of the weights, or not half of the weights, but use those splitting factors on the left chunk of the stocks and the other rest on the right chunk, and I would go chopping off the dendrogram and allocating whatever splitting factors I get based on the covariance matrix, right? So in practice, there is a package in Python called mfinlab, which has implemented this idea, right? This hierarchical risk parity idea. Oh, and I should mention that there are already this hierarchical risk parity became so famous that there are already many extensions to this technique. One of them is to actually follow the tree, right? Follow the dendrogram when you allocate. You don't heuristically divide the dendrogram in half, but you actually follow, like in a water filling technique, right? You would actually follow the paths here of the tree when you do the allocation. It's a little bit more, it's less heuristic. But anyways, getting back to the code here, I'm just downloading some 50 stocks, I guess 40 something stocks from Yahoo Finance. Everyone is familiar with that. And then the code is really straightforward. It's basically, I mean, one line of code. You create an object from this class, and then you use the allocate method with passing the prices or the log returns or the returns. It will take care of you for you. So, and then you get back the weights, right? And let's see how it performs in practice, right? So I forgot to mention, but the range here of date, the range that we are considering is from 2018. It's basically the whole 2019 year. So let's see if there was some effect here. So here's the allocation of the basic vanilla risk parity portfolio, and here's the allocation for hierarchical risk parity, right? And then we see it's kind of different, right? You see that there is a lot more weight, for example, here in these technology companies, Apple, Amazon, and Facebook, in HRP, whereas in RPP not much. So it's different. Yeah, let's see now the risk contributions. As expected, risk parity, I put everything flat. I want the same risk across all the assets, whereas I cannot control that in hierarchical risk parity. But you know, it's diversified as well. However, here on this end, there is not much risk allocated, and yeah, there is quite a lot of risk on these technology companies. But I think it's fine because these technology companies recently, they have been doing so well, very well, right? So I think it's not a problem. So let's see. So I use that data to train, right, the portfolio, and now I'm gonna do a test on the most recent data, like from basically almost yesterday, let's say 2 weeks ago, until 2 weeks ago, and we can see there is basically no difference, right? From RPP to HRP to IVP and to the uniform portfolio, we can see they do pretty much all the same, which I mean, it's disappointing to some extent, because we would expect such a fancy technique, so much fuzz around hierarchical disparity to do well during those times of crisis. But you know, it was a huge impact on the stock market, so maybe it's hard to believe that any portfolio strategy would have done superb, right, during those times. And another thing is that I just used the vanilla, right? I just used the vanilla hierarchical disparity and the vanilla RPP. I didn't include like a robust estimator of the covariance matrix, or I didn't include shrinkage in mu. So probably those things could have helped. Yeah, some closing thoughts, right? So as we've seen, disparity is pretty much a change in perspective, in philosophy. You want to allocate risk rather than capital, and that's the same thing that goes the same for hierarchical disparity. If your problem is non-convex, there is no problem. You've seen many techniques how to deal with non-convex problems, MM, SCA, and so on. And yeah, it's interesting. So hierarchical disparity has this very interesting idea of using knowledge from graph theory, which is something very hot nowadays, into a very important problem such as portfolio optimization. And yeah, we'll see how it develops. I mean, the guy, the creator of hierarchical disparity, he has been winning many awards for his paper. Apparently, he has a new job on even a better company than he was before, and he teaches at Cornell in New York. So yeah, he's been extremely successful, and it's good to learn from those people, right? And then I would very much suggest you to keep an eye on those GitHub repositories. We always like to update it with new tutorials, new features. So if you enjoy the class, if you found it interesting, and maybe you're gonna find these packages useful later on, who knows. And I guess that's it. If you have any questions, I'm very happy to answer. And as just a final saying, I loved very much my first TA experience with this class. The class was small, which is good because we can assist the students a little bit better. And I hope you had a good time taking this course. I hope it was interesting. I hope the homeworks were not didn't give you much headache. Many of you I know that did really well. And yeah, we are excited to see your projects next week. Yes. Any questions?